Okay, so previously we had talked about looking up figuring out where our variables are based upon our non-dimensional numbers, our whatchamacallit, Sommerfeld numbers, our bearing characteristic numbers. So those lines are given for particular length diameter ratios: 1/4, half, 1, and infinity, which basically anything over 1.5 is close enough to infinity. But sometimes we don't have a bearing that fits to one of those nice length diameter ratios, so we're going to need to be able to interpolate. So there's a formula given for that by the nice fellows who came up with who did the calculations for the charts. So you can use that to plug in what actual value you have, and this will give you the y dimension. So like on one of the charts, whatever y dimension it is you're looking for, that'll give you the the dimension you're going for at that particular bearing characteristic number. So yeah, bit of a complicated formula, but not exactly too onerous to do, especially if you let Excel do the work for you. But so let's kind of have a look. So if we have a journal, it's got a bearing with a 2-inch diameter and a 1 inch of length. So that'll give us an L/D ratio of half. If we got 0.0015 inches of radial clearance, so let's just figure out what our R/D is. So if our R/D is, if our R is 1 inch, and our R/C, not R/D. So for radius is 1 inch, and then our radial clearance is 0.0015. That'll be 666 for R/C. .6. Okay. And we are supporting a fixed load. That fixed load is 1,000 pounds. And the shaft is rotating at 300 RPM. So if our fixed load is 1,000 pounds, we should figure out what our P is. So our P, that's just equal to, our bearing pressure is equal to the load divided by the length times the diameter. So 1,000 pounds divided by length is 1 inch, our diameter is 2 inch, so divided by 2 inches squared, that gives us 500 psi. And then our N, you got to keep in mind that the N that we use for those charts is in terms of revolutions per second. So our N is equal to 3,000 RPM times 2 pi revolutions. No, wait, not 2 pi. We don't have any 2 pi there. We want We're still in revolutions. We're not doing radians. My bad. Force of habit. So times 1 minute per 60 seconds. That'll get us to 50 revolutions per second. Next thing we'll need is our viscosity. So we just flip over to our chart here. Let's resize this a bit so you can see it a bit better. There we go. So again, this is figure 13.6 from Juveniles. So we are operating at a temperature of 130 degrees Fahrenheit. So let's just draw a line there. Oh, that's a bit crooked. Let's draw a straight line, vertical line there. That looks a bit better. And then again, we're operating on this is SE20, so that's the second line from the bottom. And we just need to figure out what its viscosity is where that line intersects. So intersecting right there. So looking at this, keeping in mind that this is a log graph, that'll probably be about 3.1, maybe 3.2, I think. Let's go for 3.2. And again, 3.2 microrain. Okay, so where we go here. Viscosity is equal to 3.2 microrain. A reminder that a microrain, a rain is just a second. It is a pound second per inch squared. So if we want to figure out what our Summerfield number is, our S, our bearing characteristic number, Summerfield number, that is the viscosity times the rotational speed times the bearing pressure times the radius divided by the radial clearance squared. So I'll start with the 666.6 is our R over C ratio. We square that, then times our viscosity, so 3.2 times 10 to the negative 6, because it's a microrain, and that is pounds second per inch squared, times our rotational speed, so 50 revolutions per second. The seconds cancel out. And then divide that by our bearing pressure, the 500 psi, so 500 pounds per inch squared. Pounds cancel out and the inches cancel out, and we're left with a dimensionless number, which is exactly what we expect to get. So 666.6 squared times 3.2 e negative 6 times 50 divided by 500. That gives us a bearing characteristic number of 0.142. So I'm going to write that up in the top corner here and then erase all the stuff that we used to calculate that. Okay, so and then we just use that to look up what our parameters are that come into play. So we are being asked to find the minimum oil thickness, the bearing coefficient of friction, the maximum pressure within the oil film, the position of that film thickness, the maximum pressure, that's the position of the maximum pressure, the terminating position of the pressurized film, and the total oil film flow through the bearing, and then what fraction is recirculated. So let's get started. So opening up our, we can go to our charts here. So here is our chart for the minimum film thickness. So our minimum film thickness, we are working at a 1.4. So that'll be just above this line right here on the chart. So, and we are working with a length to diameter ratio of half. So we're basically at this line right here. So that corresponds to a minimum film thickness variable, H0 over C, of 0.26, looks to me. So H0 over C is equal to 0.26. Therefore, H0, solving for H0, is 0.26 times our radial clearance of the 0.0015 inches times 0.26. That gives us an H0 that is equal to 3.9 times 10 to the negative 4 inches. Oh yeah, sorry, I forgot to erase the over C. So that's our H0. So bearing coefficient of friction. Hey, they put them in the same order, not shocking. Okay, so we are looking again. We're looking at kind of just above this line here. And let's see, so the L over D for half is the second one from the top, so we're basically right there. So that looks to me like we are at 4.5. So a 4.5 is, again, the R over C times the coefficient of friction. So if R over C times F is equal to 4.5, then to solve for our coefficient of friction, then we just need to take our F and divide it by the R over C, which is 666.6, and that'll give us our F. So why did I put 4.6 there? 4.5. Too many sixes on the brain. 4.5 divided by 666.6, that gives us, we're working with the coefficient of friction of 0.00675. Now, what's the next thing we're looking for? The maximum pressure within the oil film. Hey, look, that's the next one too. So, similar idea. We're just above this line. And this is the second line from the bottom this time. So, that intersection to me looks like, oh, no. Accidentally clicked on the wrong spot. There we go. Looks to be like exactly 0.3. So again, 0.3 is equal to the bearing pressure divided by the pressure in the film maximum. 0.3 is equal to, so our bearing pressure is 500 psi. And then our Pmax. So solving for our Pmax, that is just multiply out the Pmax, divide by the 0.3. That gives us a Pmax of 500 divided by 0.3, which gives us a Pmax of equal to 1.66 KSI. Okay, so I got a maximum pressure within the oil film, position of the maximum film thickness is our next one. Yep. So again, kind of right here on that line there. Second one from the top again. So looks to be right about there where that intersects. So scrolling over here, that to me looks like we are at probably about 37.5. So 37.5 degrees is what it is. So that's the phi value. It was what they're using to denote that. So phi is equal to 37.5 degrees. Okay, what else? That's the next one. So that's the position of the maximum of the minimum film thickness. The position of the maximum pressure is our next one. I gotta rotate our chart here. There we go. So this chart combines both the terminating position of the film and the position of the maximum film pressure on the same chart. The position of the maximum film pressure is the dotted line. The terminating position is the solid line. So okay, so again 0.14, right about there. 0.142, obviously the 0.2 we can't really tell on these charts. So and we are looking for let's see. Yeah, so the yeah, so a dotted line is the position of the terminating position of the film. So we're looking for the solid line first, the Pmax one. So that is this. That's this line here. So the position where that intersects is, let's zoom in a little bit so we can kind of see it there. Okay. So to me, when I move over here, this looks like, let's see. Okay, so between 15, I got this section here that's between 15 and 20 degrees. So these are half-degree increments that are given. So that looks to me like we are looking at 16.5 degrees. So theta P max. Theta P max is equal to 16.5 degrees. I realize that's under my face there. So next up, the line for the position, the terminating position of the film. That's this one here. So where that intersects. That looks like this. Drew that a bit crooked. 50 degrees. Terminating position of the film. Theta. What was the nomenclature they used for that? Theta P naught. Is equal to 50 degrees. Okay. Next up, total oil flow through the bearing. So we have I need to unrotate it. Okay, so we got our chart here. Zoom out a bit more so you can see. So our flow variable, once again, that was a bit off center. That's even worse. Let's try it with the mouse. There we go. That's better. Okay, so we got our bearing line for the bearing characteristic number, and our L over D of 1/2 is going to be the second line from the top. So we'll zoom in a bit more to make that clearer. And we're looking at right here for the intersection, which when we move over here, 5.1, 5.2, 5.25. 5.25 is going to be our Q over R CNL. So if Q over RCNL is equal to 5.25, then our Q is going to be equal to, moving this stuff over to the other side, 5.25 times RCNL. So 5.25 times our radius of 1 inch times our radial clearance of 0.0015 times our rotational speed of 50 revolutions per second, so per second, times our L of 1 inch. So we got 3 length terms there and a per second term there. So we're going to be in inches to the third per second, cubic inches per second. We'll multiply that out, so that gives us a Q value of 0.39. And here, let's put that somewhere else. Q is equal to 0.39 cubic inches per second. And then, so that's a total oil flow through the bearing. So basically kind of, how much gets swept in, how much is being used to form that wedge. Some of it gets recirculated and some of it is side leakage. So the next chart gives us our flow ratio. So that's that's a ratio of the side leakage to the yeah, basically a ratio of the side leakage to the normal flow, or the total flow, not normal flow. So again, just draw our line for the 1.4. We're looking there. We got our half line here, our L over D of a half. That's right there, which means that our flow ratio here looks to me to be 0.5. Sorry, 0.82. No, 0.84. Yeah, 0.84. So that's a fair amount of side leakage going on there. So our that is the fraction. The question asked for what fraction needs to be introduced to make up for side leakage and what fraction is recirculated. So the fraction that needs to be used to make up for the side leakage is the 0.84, whereas the remainder is the portion that's recirculated. So 1 minus 0.84 is 0.16. So 16% of the fluid that enters the wedge makes it back around, whereas the rest leaks at the side and then needs to get reintroduced in some other manner. So yeah, that'll be how we kind of look up those things on our charts.